So this video is on functions and modeling. So we're going to start with talking about what is a function. So in a math class, you probably, when you think of a function, you probably think of like f of x equal to, let's say, x squared. Right? So this is typically a nice formula for the function. It has a graph. Right? The way we make a graph is we have input and output. And so if you plug in 0, right, you can make a table over here. If you plug in 0 for x, the output for y is 0 squared, which is also 0. If you plug in 1, it's 1 squared, which is 1. If you plug in 2, it's 2 squared, which is 4. If you plug in 3, it's 3 squared, which is 9. And so you can draw a graph of this. It looks like this on the right. And then you can plug in the negative numbers too. So if you plug in negative 1 squared is 1, negative 2 squared is 4, and so on. So you get the same graph on the left. And so that's a graph of x squared. And so these are three basic representations. You have a table, you have a graph, and you have a formula. You can also describe functions in words too. Now the definition of a function, or definition given in most pre-calculus textbooks, is something like a function is a rule that assigns to each input value a single output value. Now what's important about this definition is that it assigns a single output value. So for example, you can draw a graph of something that's not a function. Right? So this is my x and y axis. If you draw, let's say the simplest thing is probably just a circle. If you draw a circle, so here's my circle, this does not represent a function because when you plug in something, so just plug in this number, let's say whatever is right here, let's say it's 1. If you plug in 1, you get an output here and you get output there. So this is not representative of a function, so not a function. Sometimes we say it does not pass the vertical line test, which means if you draw a vertical line, if it hits the graph more than once, and so there's my, let's just draw a vertical line here, so there's my vertical line, you can see it hits it twice, right, then it's not a function. Right, so a graph of a function can only hit a vertical line at most once. So you have a couple problems on your homework to kind of test you on this. You can also make tables that are not functions. It's pretty easy. So you have x and you have y, and you'd say, okay, well 1 goes to 2, and then 1 also goes to 3. So this is an example of a table that's not a function. What's next? Okay, so let's take a look at example 1. All right, so in example 1, what we want to do is you want to use your calculator to recreate the following representations of a function. So we want to make a table, a graph, and a formula. So if you have your graphing calculator, let's take it out. And it's real easy to graph the formula. You just hit y equals. So if you hit y equals here, I'm going to clear this out, and you're going to plug in this formula, 240x. And then I'm going to take away 2x squared. So minus 2x, I need a 2 here, so 2x squared. Right, so I'm just plugging this formula into y1. I want to make its graph. Now notice if you just hit the graph button, it's probably not going to give you a very good picture because you really didn't tell it where to look. So what I need to do is I need to change the window. So if you hit the window button, this is going to set up your window. Now how do you want to make your window? Well, you can look at this information and kind of figure things out. So you can see that there are no numbers listed here, but there are numbers over here. So the inputs go from 0 to 120. So I'll make my x min 0. and I'll make my x max 120. And then you can see my y min is 0 and my y max is 7,200. So I'll go down here. I'm just looking at these numbers on the outputs here. Those are the y values, and it looks like 0 is the minimum and 7,200 is the maximum. And now if you hit graph, you'll see you basically get the same graph over here. So when you're graphing something, you always have to know where to look. So I have y equals, I have the graph. Now this is a table, so you can see behind the graph button or above the graph button there's a table button. So if you hit second graph, it pulls up your table. Now this table and this table are not the same. This one is 0, 1, 2, 3, 4, 5, and this one's 0, 20, 40, 60, 80. So we want to make them look the same. So to do that, we have to change the table. And if you look right here above the window button, you'll see table set. So you hit second window. And we'll start our table at 0 because this table starts at 0. And then down here below it, this little triangle means delta, which means the change in. So this is how's the table changing. So we don't want to change by ones. If you notice, the inputs are changing by 0, 20, 40, 60, 80, so by 20 each time. So we'll hit 20 here. And then, if you go back to second graph, go back to the table, you'll see that these outputs are the same as those outputs. So now we have the formula right there. We have the graph right here. And we even have the table represented right here. So that's how you make a table, a graph, and a formula with your graphing calculator. All right, so those are the representations that we're most commonly used. We'll talk a little bit about formulas in terms of words when we come down here and do the modeling stuff. But first, let's take a look at what's called function notation and literacy. So let's do this. This is probably best done with an example. So here's our example, example 2. And they give us two graphs, f and g. So f is the graph in sort of pink right here, and then g is the graph in blue. And we want to find two things, f of 2 and g of negative 2. So the functional sort of notation and literacy part, right, f of 2 is what's called functional notation, and understanding what to do is the literacy part. So if you want to find f of 2, the way this works is that 2 is an input value, and over here we're going to put the output value. So the inputs are always along the x-axis. So you have 0, maybe we should fill these in. That's 1, that's 2, that's 3, that's 4. So f of 2, here's 2, you would go up here and you'd look at the graph, it's the pink one, and there's that point in the graph. So it also has height 2. So if the input's 2, the output's 2. Whereas g of negative 2, so negative 2 is the input. You can kind of remember that because it's on the inside. So the input's always on the inside, the output's always on the outside. And so let's label these. This is negative 1, this is negative 2, this would be negative 3, this would be negative 4. And so you go to negative 2, and then you go up here, and then g's the blue graph, so it's this height right here, which is what? Height 1. So g of negative 2 is equal to 1. Right, so this is sort of working with functional notation, and the literacy part is trying to figure out what it's actually asking you to do. All right, so for what, in part B it says, for what x values is f of x equal to g of x? So here, it's not asking when are the inputs equal, it's asking when are the outputs are equal, because f of x is an output and g of x is an output. So when are these two outputs equal? You look, and I actually already have dots there, but it's right here and right here, and you're looking for the x values, which are the inputs. So we look along here and we say, oh, x equal 2 and x equal negative 2. So there are two x values that make the outputs the same. So x equal 2 and x equal negative 2. And then the next question says, find the solutions to the equation f of x equals negative 1. All right, so again, this is quantitative literacy and also using functional notation. So here's the functional notation f of x equal to negative 1. You have to realize this is output, so what it's saying is for what inputs give you an output of -1. So output -1, you don't look along the horizontal, you look along the vertical. So here's -1. And you're looking for the outputs for f, and so f is, again, this pink sort of graph. And then those two values are where? Let's use blue. So those two values, when is f -1? Well, it's -1 right here, and it has height -1 right here. So the corresponding x values are -3 and +4. So the two solutions in this case would be f equals -3 and x equal to +4. Sometimes on MyMathLab, what they'll do is they'll have you separate answers by commas. So you could also write this as just equal to -3, and then you just put a comma as for like the next answer would be +4. All right, so the last thing we want to do is we want to talk about what's called the domain and the range of a function. So if you have a function, you're always going to have a domain and range. You should remember that the domain is a set of inputs, or input values, let's say. So it's a set of input values. Whereas the range of a function is a set of output values. So the domain is input value stuff, and so it's always x stuff, whereas the range is output value stuff, so it's always y stuff. It's actually very easy to remember because it's all alphabetical. dr, input, output, and then x and y. So that's how I typically memorize or remember what these things actually are. And so now we want to find the domain of G. So let me erase some stuff here. Let me erase this and we'll fill it back in so we can get a clear picture. So if we want to find the domain of G, basically you're looking for all the input values for the function G, and then when you're looking for the range, you're looking for all the output values. So let's label this again. You go 0, 1, 2, 3, 4, and then -1, -2, -3, -4. And we'll do the domain in green, because green is good. Domain is good and range is bad. So for the domain, we write D equals. And if you look at this graph, you'll say, okay, input values. Well, if you look at -4, you'll see above -4 there's an open circle, which means do not include. So we'll start at -4, but we'll use a parenthesis here, which means don't include -4, but start there and go all the way. So above all these input values, you have output values until you get to the number 3. So when you get to number 3, you have a closed circle there, which means do include. So we end at 3, and do include, instead of a parenthesis, we'll put a square bracket. This is called interval notation, and what it means is all the numbers between -4 and 3, and including 3. This actually has a longer explanation, although we don't really like to write this. This is actually the set, and we would write the set of all x, and this means an element of the real numbers, such that what? Such that -4 is less than x is less than or equal to 3. So over here, this interval notation is sort of a shorthand notation for all of this. You can understand why we like to use a shorthand notation, because this right here is a little bit too complicated for us right now at this time. As we get more comfortable with this sort of stuff, you know, maybe a year down the road or so, you'll start writing things more like this. But for right now, we're just going to use interval notation. So that's the domain, the possible input values. And then, of course, we also want to find the range. And now for the range, instead of looking along the horizontal, you just look along the vertical. So on the vertical, let's relabel these. You have 0, 1, 2, 3, and you have 4. And then you have -1, -2, -3, and so on. And so we're going to look along the vertical, and again, we want to find it not for f, but just for g. So here's g right here in the blue. And you can see that the output values start right here. They start right here. And I think that's probably the value at 1/2, about some nice number between 0 and 1. And they go all the way up. So all the way up, all the way up, all the way up to here. And it's because this point is closed, you include it. And so the output values would be 1/2 to positive 4 and including positive 4. You can read it off the graph right here. I should have also shaded in the domain so you can see how that works a little bit better. So the domain goes from -4 to 3. So you can see here you start at -4. It's open sort of parenthesis because you don't include the point. Again, we're working with G, which is in the blue, so you don't include it because it's open. And all these points have a graph above it. You can see these are all points in the domain until you get to 3 right here. I went a little bit past 3. So until I get to right here at 3, and then you look above 3 and you see it's a closed circle, so you include it, and so that would be from -4 to 3. So this is our domain and our range. The next problem we want to look at has to do with finding the domain of a formula. Now typically to find the range of a formula you're going to need a graph, but the domain of a formula is not too difficult. So there are basic things that limit what you can put into a formula for a function, at least the formulas that we're working with. So what limits the domain? So limits of domain. There are basically 3 things we have to worry about in this class. The first thing is you can never divide by 0. So if you have a function, make sure whatever is in the bottom is never equal to 0. The second thing is if you have a square root, make sure whatever is inside here is always bigger than or equal to 0. This is because we don't want to deal with numbers like the square root of like -1. This is what's called an imaginary or complex number. And complex numbers we don't want to worry about. We just want to worry about real numbers. Right. And this is actually for any even root. So 4th root, 6th root, 8th root, any even root, we want to make sure whatever is inside there is bigger than or equal to 0. Although most of the time we'll just be working with square roots. Odd roots, it really doesn't matter. You can take the cube root of -8. It's equal to -2. So you don't care about odd roots, just the even roots. And then the third thing, which we're not going to worry about right now, but if you have a log function or in particular an ln function, whatever is on the inside here needs to be bigger than 0. But again, we're not going to worry about this one right now. We'll worry about it when we study log functions. So here, when I look at this function, I ask myself first, is there a denominator? So 1. Do you have a denominator? And I say, oh, of course you have a denominator. You have this x plus 5 here. And so you need to make sure that x plus 5 is not equal to 0. And so we subtract 5 from both sides. And so we know that we cannot have x cannot be equal to -5. So that's the first number we have to throw out of our domain. So down here what I'll do is I'll draw a number line and I'll put a circle here at -5, which means do not include -5. And then the second thing we have to worry about is if there's a square root. So do you see a square root? And you say, oh yeah, here's a square root. And then for the square root, what you need to worry about is the inside. So you need to worry about this piece right here. So make sure the inside, which is 2 minus x, make sure that is always bigger than or equal to 0. If it's not, you'll have a complex number, which you don't want. You only want to work with real numbers. And so what we can do is we can subtract 2 from both sides. And so we get -x is greater than or equal to -2. And so the idea is that when you work with an inequality, it's the same as working with an equality, with one difference. If you divide or multiply by a negative number, you have to flip-flop that inequality sign. So in order to get -x to be positive x, we'll multiply this both sides here by -1. So you get x, and then less than or equal to, and then -1 times -2 is positive, not 1, but positive 2. So x is less than or equal to positive 2. Sometimes students ask me the question, how do you know that this symbol is less than? And I tell them if you just turn it a little bit, it looks like an L. Whereas then the other one has to be greater than. Right? So this is less than. And then the other symbol means greater than. And so here x is less than or equal to 2. Well, here's 2 right here. And less than or equal is to the left. And so equal means you close bracket. We're going to jump over -5 because we had to throw that one out. And so that is my domain. All these numbers between 2 and -5, and from -5 all the way to the left, so all the way to like -infinity. So my domain D is equal to, we would write from -infinity, right, so that's a symbol for -infinity. It's like a sideways 8 to -5, in parentheses, union, right? So not close bracket because you don't want -5 in it. And then parentheses again, -5 to 2, and then close bracket instead of parentheses because you want to include positive 2. And so that's the domain of this function g of x. So that's how we kind of work with formulas and finding the domain with a formula. We're going to move on to the last topic, which is modeling. So let's look at just an example, and we'll talk about how we do sort of modeling problems. So on example 4 here, it says you have 240 feet of fence to enclose a rectangular region along the side of a barn. So you have a barn here. And we want to express the area as a function of one of its sides. Right, so this is considered what most students consider a word problem. And the idea is you can make a formula or find a function, from this word problem. The way I typically solve word problems is I do a 4-step sort of procedure. We're going to do what's called a P and E, and there's often 2 other steps, S and T. S and T. Now we're not going to do all 4 steps today because this is really just a P and E problem. The P actually stands for picture. So the idea is you want to take the words and sort of draw a picture of what they want you to do. Basically write down all the important information. And then we can come up with an equation or a function or some sort of expression that we can use to solve the problem. And then we can solve it. And a lot of times we can even test our solution to make sure we actually did it right. Now today we're just going to do these first 2. Picture, equation, solve, and test. But you should know that this process doesn't just work for math problems. It works for any problem in general. So if you have an issue with your sort of finances or something, what you would do is kind of write down, what is your issue? What's your problem? Where are your finances at? So you might make a table, you might draw a graph. But you would write down that information and get it in one spot and then put it in a way so you can access that information kind of all at once just by looking at it. And then your equation, would be sort of how are you going to solve this financial issue, this financial situation. You would come up with a plan, basically. In our course, it's like an equation or a function, but you'd want to come up with a plan. And then to solve, you would actually implement that plan. And then when you implement that plan, you better have a way to test it to see if the plan's actually working. So, if you implement your financial solution to your problem, you probably check it after a couple months to see if it's actually solving that problem, if it's actually doing anything of worth for you. But for us, the picture is relatively easy. This is sort of a geometric word problem. So you want to draw a rectangle. So here's our rectangle. And then along one side of this rectangle, there's a barn. So let's put a barn right here. It doesn't matter where you put the barn. I just usually put it on the left. So there's a barn right here. And so you want to enclose this rectangular region. And it tells you how much fence you have, 240 feet of fence. So the units are always important in these cases. So you see it's in feet, and so that's the amount of fence that you have. It's not the area that you need to enclose. If it was area, it would say 240 feet squared, right? Not just 240 feet. So 240 feet just means the amount of fence that you have. So if you were to go buy this amount of fence at Lowe's, you'd say, hey, I need 240 feet of fence, and that would be the amount of fence that you would purchase. What else? And then you want to express the area as a function of one of its sides. So find, always write down what you need to find in the problem. So you need to find the area as a function of, and one of its sides. So let's label a side. Let's call this side x, which means this side is x, which means this side, which we don't know, it's a rectangle, right? So it may be shorter, maybe longer, so we'll call it y. So let's find it as a function of x. So very important, always write down what you're trying to find. And then so for the equation, if you wrote down what you're trying to find, it's pretty easy. You're trying to find the area, and you're trying to express it as a function of x. So my first step would be just try to write down a formula or an equation for area. So you know area, it's length times width. So this would just be x times y. And so there's a formula for the area. Now it's not a function of x, it's actually a function of x and y. And so what we need to do now is we need to somehow get rid of y, and that's where this 240 feet of fence is going to come into play. So I know if you have 240 feet of fence, and this side has x feet, and this side is x feet, and this side is y feet, and remember you don't need to count this side because it's part of the barn. What you have is x plus y feet of fence. So you have 2x plus y feet of fence, and you know that's equal to 240, so when you add all those sides together, you should get 240. And then you can solve this for y, so we'll subtract 2x from both sides. And so what does that give us? It gives us 240 minus 2x is equal to y. And what we can do now is we can take what y is equal to, 240 minus 2x, and we can plug it in right there for y, because they're really the same thing. So we call this substitution. This is something we do all the time, especially if you travel to another country or something. So if you go down to Mexico, sometimes you'll take your dollars and you'll substitute them for pesos. Or when you come back, you'll take those pesos and you'll substitute them for dollars. So like the last time I went to Mexico was quite a few years ago. I do remember that $1 was the same thing, was equal to 13 pesos. Right? So even though 1 is not 13, when it's $1, it's equivalent to 13 pesos. Just like here, like I know 240 minus 2x isn't a y, right? There's no letter y over here, but it's equal, it's equivalent to y. So what we can do is we can just replace them. So right here I'll write equals x, and I'll plug in, I'll put a parenthesis 240 minus 2x. And so that's my a. And so now you're basically done. A is equal to x times 240 minus 2x, so it is a function of x. If you want to make it look a little bit nicer, you can multiply through here by x and get 240 x minus 2x squared. And so that would be my final answer for the area as a function of one of its sides. What you want to notice is that, if you change x, you change the area, and this is actually the problem we sort of started with. So if we go back up to the first sort of example that we did, you can see that the formula that I put into my calculator was the same formula that we got in that example. And here's a graph of that formula. So what's happening is as your inputs change, right, this is your x stuff, your outputs are changing. Now remember, on these outputs, it's not y, it's actually the area. And you can see as x changes, the area gets larger and larger and larger, but then it hits a maximum, and then the area gets smaller and smaller and smaller. So later on we'll do these types of problems, and one of the solving parts will be find the x value, right, find the length of that side of the fence that maximizes the area enclosed. So you'll have to find this maximum point and find the input value that leads to it. And you can actually see it over here. It turns out to be 60, and the maximum area is 7,200 was it feet? Yeah, feet squared. But we'll talk about that later.